Okay, in this video, I'm going to show you a technique for evaluating integrals. This is called a indefinite integral. There's no limits of integration here, so it's called an indefinite integral. We've done this before. Antiderivatives. This is a pretty complicated one here. At least it looks complicated right now. The substitution method is introducing a new variable, which we're going to use. We're going to make a clever substitution into this integral here, which is going to simplify it to something that we can determine its antiderivative quite simply. So we're going to introduce a variable. The variable I'm going to use is u. So we're going to let u equal something in terms of x. Now, what do we have here? We have x multiplied by bracket x squared plus 9 to the 5. If we let u equal x squared plus 9, and if we were to differentiate u with respect to x, so I'll just write that symbol du over dx, we get 2x. So now what I'm going to do is multiply both sides by dx, and look what happens. Du is equal to 2x multiplied by dx. Then I'm going to divide both sides by 2, and I get 1/2 of du is equal to x dx. Now, x dx appears here. There's an x multiplied by dx here on this side here. So that means I can substitute 1/2 of du for this x dx. And I'm going to do that. Let's see what happens here. So instead of the x and the dx, I'm going to replace it with 1/2 du. Now the 1/2 I'm going to write on the outside of the integration symbol here because it's just a constant. So the x dx now will be replaced by the half out here and a du. So I'll write the du right here. And now I'm left with this bracket x squared plus 9 to the exponent 5. Well, u equals x squared plus 9, so I'm going to replace this x squared plus 9 with u. And I still have that exponent of 5 here I have to write. So here we go. We have a new antiderivative, which is quite easily computed. We use the power rule here. We add 1 to the exponent. Add 1 to the exponent, we get 6. And then we divide by 1/6. Or sorry, we divide by 6. So we go with 1/6 of u to the exponent 6 plus c. Don't forget our constant, which we need to put with indefinite integrals. So 1/2 times 1/6 is 1/12. U to the 6 plus c. Now we want to replace u now at this point with x squared plus 9. So this is equal to 1/12 of x squared plus 9 exponent 6 plus c. So there you have it here. We have a antiderivative in terms of x. In this example, we're going to let u equal the x cubed plus 3x squared plus 12. Now when we differentiate with respect to x, we get du over dx is equal to 3x squared plus 6x. Let's multiply both sides by dx. So here we get du. This multiplied by dx all right here, but I'm going to factor out a 3 here, so we'll have 3x squared plus 2x. And then I'm going to divide both sides by 3, so we'll get 1/3 du is equal to x squared plus 2x dx. Okay, so let's make a substitution here. We have x squared plus 2x multiplied by dx, and our substitution tells us that that's equal to 1/3 du. So I can replace this numerator with 1/3 du. I'll put the 1/3 outside the integration sign here, and I'll replace all of this with du. I'll write du to the side here, and the numerator, I'll just put a 1 here. The denominator we replace with u, and this is to the 6, so we have to put the 6 as well in there. Okay, so this is a simpler antiderivative. Let's rewrite it first using a negative exponent. So 1 over u to the 6 is equivalent to u to the negative 6 du. And we're just going to use a basic power rule here. What we do is we add 1 to the exponent. So negative 6 plus 1 is negative 5. And then we divide by negative 5. And don't forget the 1/3 here. So it's going to be 1/3 multiplied by that. And also don't forget the plus c, because this is an indefinite integral. Let's keep on going here. 1/3 multiplied by 1 over negative 5 is negative 1/15. U to the negative 5, I'm going to write as u to the positive 5 in the denominator, plus c. And then the last step, I'm going to replace the u with x cubed plus 3x squared plus 12. And don't forget to the exponent 5. And a plus c. So there you have it. There's your antiderivative. Okay, the next example, the antiderivative of tan theta d theta here. The first thing I'm going to do is I'm going to rewrite tan theta using an identity. Tan theta is sine theta divided by cos theta multiplied by d theta. Okay, so what am I going to use my substitution here? I'm gonna let u equal cos theta. Then I'm going to differentiate with respect to x. So with respect to theta, actually, d theta, and the derivative of cos theta is negative sine theta. Then I'll multiply both sides by d theta, so I'll get du equals negative sine theta times d theta. And one more step here, I'm going to divide both sides. Actually, I'll multiply both sides by negative 1, so I'll get negative 1 du, and we'll get sine theta d theta. Okay, so now let's look back here. We have a sine theta d theta in the numerator here, so I can replace sine theta d theta with negative 1 du. I'm going to put the negative 1 outside the integration symbol here, and I'm going to replace that with du, but I'll put it 1 over there in the numerator, and I'll put the du to the right here. And we have cos theta in the denominator, but we define u as being equal to cos theta, so we're going to write down u here. Okay, so here we go. This antiderivative is quite simple. The antiderivative of 1 over u is just ln u. So this becomes negative 1 times ln the absolute value of u plus c. And now we're going to replace u with cos theta. This is the absolute value of cos theta plus c. So we're done here, but if you were to look up the antiderivative of tan theta d theta in the textbook. You're not going to see this. I'm going to show you what you're going to see. Um, let's just use a rule here or a property of logs. This -1, I'm going to write up here. So this becomes ln of cos theta to the -1. And then a negative exponent applied here. I'm going to write it as 1 over cos theta plus c. And one more thing. This is the reciprocal of cos, right, is defined as secant. So I'm going to rewrite with this as the ln of the absolute value of secant theta. And that's what you would find if you looked it up. If you looked up the integral of tan theta in a textbook, you'll see ln of the absolute value secant theta plus c. Okay, our last example here, we're going to let u equal 5x plus 1 du by dx equals 5. Then we multiply both sides by dx and then divide by 5, and we get 1/5 du equals dx. Okay, so we have a dx here. We'll replace that with 1/5 du. 1/5, I'll write to the left here. Dx gets replaced with du. Square root of 5x plus 1 becomes the square root of u. So I'll write that as u to the half. But we still have this x here. We have to substitute and replace that in terms of u. So what I'll do is rearrange this, isolate x, to be u minus 1 over 5 is equal to x. So now I can replace x with this. So u minus 1 over 5. Okay, so now comes some simplifying. This is going to be 1/25, right? I'll just take this, divide by 5 to outside here, multiply by 1/5. And then I'm going to use a distributive property here. U multiplied by u to the half is u to the 3/2. 1 multiplied by u to the half will be u to the half. Now I'll use power rules to figure out the antiderivatives. So we add 1 to 3/2, we get 5/2. And we need to divide by that exponent, so that flip and multiply here, we get 2/5. Minus, add 1 here, we get 3/2. And we need to divide by that exponent, so that flip and multiply again, we get 2/3. Okay, plus c. Let's use a distributive property here. So this will be 2 over 1/25 u to the 5/2 minus 1/25 times 2/3 is 2 over 75 u to the 3/2 plus c. And finally, we need to reintroduce x. So this becomes 2 over 1/25 u is 5x plus 1, 5/2, minus 2 over 75 u is 5x plus 1 to the 3/2, and plus c. So there you have your antiderivative.